Welcome to the journey between science and the silence of the universe. Imagine yourself lying under a starry sky where each tiny light is a giant flame quietly writing the story of life. In tonight's adventure, we will explore a miraculous secret: how the stars, those fiery hearts in distant space, can create the very elements that make up your body and the world around us. Before we begin, I truly hope you will subscribe and stay with us until the end of the video. Not only so you won't miss the next journeys, but also so that our small community can grow together, listening to and admiring the universe in a gentle, relaxing way. Thank you for being here, and now let's step into the secret of the stars. When the universe passed through its primordial era, clouds of hydrogen and helium were gradually pulled together by gravity. At first, they were just small ripples in the vast ocean of space. But over millions of years, they gathered, became denser, heated up, and finally formed the first stars. It was in these great torches that the true formula of the universe began to reveal itself. Imagine each star as a giant forge, where gravity relentlessly squeezes hydrogen in the core together. As the temperature rises to millions of degrees, a miracle happens. Protons, which normally repel each other due to their like charges, are now forced close enough that the strong nuclear force, one of the four fundamental forces of nature, binds them together. The result is a burst of nuclear fusion. Two hydrogen atoms combine to form helium. This may sound simple, but it is the turning point of the entire universe. Because in that process, a portion of the hydrogen's mass is transformed into energy, released as light and heat that we perceive as the shining of the stars. The light you see when you gaze at the night sky is the testimony of that elemental creation process happening continuously. Over time, as the hydrogen in the core gradually runs out, the star enters a new stage: burning helium. At this point, the reaction becomes more complex. Three helium nuclei fuse together, resulting in a carbon atom, a leap in atomic structure. Carbon is not just an ordinary element, it is the foundation of organic chemistry, of life as we later came to know it. From the cores of distant stars, the first seeds of biology were sown. But the story does not stop at carbon. As the star grows older, its core becomes hotter and more compressed, opening the way for new reactions. Carbon combines with helium to form oxygen. With more pressure and temperature, oxygen fuses to create neon, magnesium, silicon, and so a long chain of reactions unfolds, each step opening a new chapter in the universe's recipe book. Imagine yourself standing in this cosmic kitchen. Hydrogen is flour, helium is water, and gravity is the tireless pair of hands kneading. Over time, those basic ingredients are baked, transformed, and gradually become a diverse menu, an ever richer periodic table of elements. What began with only three components has now evolved into dozens of different atoms, each playing its own role in the cosmos. However, not every star can cook to the very end. Smaller stars, like our sun, stop at producing carbon and oxygen. They lack the necessary energy to continue fusing heavier elements. Yet in that modesty lies a unique greatness. Because carbon and oxygen are the fuels for rocky planets, for water, and for life. On the other hand, massive stars, many times larger than the sun, have the power to push this process much further. In their fiery cores, temperatures can reach billions of degrees, enough to fuse even heavier elements like silicon or iron. Here, we reach a natural boundary: iron. Iron is a special element. When reactions produce iron, they no longer release energy. Instead, they require energy to continue. This means that the star has reached its ultimate limit. Like a chef with no new ingredients, the star comes to its fated end. Gravity begins to prevail, crushing the star into itself, and then a supernova explosion occurs. It is the supernova that is the climax of the story. In that brief but violent moment, temperature and pressure reach their peak, enough to forge the heaviest elements the periodic table can offer: gold, platinum, uranium. The precious metals we cherish in jewelry, technology, or energy were all born in those catastrophic bursts. And from that explosion, all those elements are flung into space, blending into cosmic dust and gas. New clouds of matter form from the remnants of the supernova, continuing the cycle, giving birth to new generations of stars and planets. From those fragments, our Earth was built, and on Earth, life began. When you take a deep breath, the oxygen in your lungs was once forged in the core of a star. When you look at a golden ring, It is a surviving memory of a distant supernova. And when you place your hand over the heart beating in your chest, remember that the iron in your blood was once the result of a star that burned itself out and exploded. This is not just dry science. It is a poetic connection between us and the universe. Every element in your body is a witness of a grand journey, a note in the long symphony of the stars. And that is why, when we gaze at the night sky, the feeling is not just admiration, but also a reunion, a return to our very origins. If hydrogen and helium are the starting pieces, then gravity is the patient hand that arranged them into the right places to begin the great game of the universe. When a young star enters its mature stage, it is like a chef who already has a secret recipe, nuclear fusion. From here, the story is no longer just about hydrogen and helium. Each advance in the cosmic furnace opens a new level of the periodic table, as if each page in nature's great cookbook is being turned. Let's begin with hydrogen fusion, the foundational engine of most stars. In the core of the sun, billions upon billions of hydrogen atoms are compressed each second to form helium. Every tiny reaction is like a quantum leap of matter, where mass is traded for pure energy. Thanks to this, the sun can shine for billions of years, enough to sustain life on Earth and to write the first chapters of biological history. But hydrogen is only the warm-up. As the supply in the core gradually depletes, the star moves on to a tougher recipe, fusing helium nuclei. This process is called the triple alpha reaction, 3 helium nuclei combining to form carbon. The miracle lies in the fact that carbon is the very cornerstone of all organic life forms we know. Without this reaction, there would be no cells, no DNA, no life contemplating the universe. But the cosmic kitchen does not stop there. With one more helium nucleus, carbon turns into oxygen. From here, the path opens up for essential elements: neon, magnesium, silicon, sulfur. Successive layers of reactions form an onion-like planetary structure, each layer cooking its own specific ingredient. This spectacle inside massive star physics is truly magnificent. Interwoven shells, each a small kitchen, all operating together to prepare the elemental feast. In stars of enormous mass, this process unfolds much more quickly. A star dozens of times larger than the sun may take only a few million years to complete a journey that the sun would need tens of billions of years for. They burn their fuel furiously, like impatient chefs always turning the flame to the maximum. The result is a dazzling brilliance, but the price is a short lifespan. In contrast, red dwarfs, small but frugal, burn hydrogen so slowly that they can outlive even the current age of the universe. What is noteworthy is that every element produced does not remain locked inside the star. Once a star completes its recipe, these elements are released into space, weaving the fabric of planets, oceans, and even your body. When you breathe in oxygen or look at the rock beneath your feet, you are directly interacting with the products of billions of years of stellar cooking. However, with iron, everything changes. Iron is the stopping point, the dead end of stellar alchemy. Why? Because fusing nuclei lighter than iron releases energy, but trying to fuse iron consumes more energy than it creates. A star can go as far as iron, but it cannot take one step further through ordinary fusion. When an iron core forms, the balance between outward pressure and inward gravity collapses. Within seconds, the star implodes upon itself. That moment opens one of the grandest events in the universe, the supernova. This explosion is so intense that it not only tears the star apart, but also creates elements heavier than iron: gold, uranium, lead, elements that enrich the world and even determine humanity's technological future. Without supernovae, there would be no gold in wedding rings, no iodine in your thyroid, no rare earths in your phone. Imagine an explosion so powerful that, for a moment, it shines brighter than a galaxy containing hundreds of billions of stars. That immense energy not only destroys, but also sows the seeds of creation. The debris, packed with new elements, is blown into space, wandering for millions of years until it gathers into nebulae, from which new generations of stars are born. It was in just such a cloud, rich in stellar ashes, that the sun and earth came into being. Thus, you and I, every molecule within us, are the direct results of violent stellar deaths billions of years ago. Your bones contain calcium from a collapsed star. Your blood flows with iron forged in a distant stellar core. Even the gold on your hand was once the final breath of a colossal explosion in the darkness of space. When you understand this, the light in the night sky is no longer just distant dots. Each star becomes a witness, a kitchen, a great machine that has written the next chapter of life's story. And when you lift your head to the sky, you are not only observing a faraway past, you are looking at the chemical history of your very own body. Carbon, a humble element yet carrying the power of an architect, appears as an unexpected gift from stars gradually exhausting their breath. It is not an element easily formed. Nuclear fusion must overcome unimaginable barriers. Three helium nuclei, the alpha particles, need to collide and merge almost simultaneously to create a carbon nucleus. The probability is exceedingly small, yet when billions upon billions of reactions occur in the stellar furnace, the impossible becomes inevitable. It is this systematic rarity that makes carbon a bridge between simplicity and complexity, between a barren universe and abundant life. What makes carbon special is not only its origin, but also its character in chemistry. A carbon atom has four valence electrons, like four flexible arms that can bond with countless partners. It forms straight chains, closed rings, crystal lattices, and innumerable rich molecular structures. Within every living cell, carbon is the framework for DNA, for proteins, for fats, and for carbohydrates. In other words, the creativity of carbon is the creativity of life. If hydrogen and helium are the fabric of the universe, then carbon is the pen that begins writing the first lines of the story of life. But carbon does not go alone. As the star continues to squeeze its core after the carbon-forming stage, pressure and temperature rise, and carbon nuclei combine with helium to form oxygen. Thus, the two central elements of biology, carbon and oxygen, are born almost side by side in the stellar fire. Oxygen, accounting for about half the mass of our bodies, is the element of breath, of water, of minerals. From a certain perspective, one could say the human body is a blend of carbon, the chemical skeleton, and oxygen, the stream of energy. Both were written in stars that died billions of years ago, then scattered across the galaxy by stellar winds and supernova explosions. Continuing the journey, large stars also produce neon, magnesium, silicon, and sulfur. These elements are rarely praised in literature, yet they play a fundamental role in building planets. Silicon, together with oxygen, forms quartz, rocks, and planetary crusts. Magnesium is an important component of minerals and directly participates in biological processes, such as binding with chlorophyll in leaves to capture sunlight. Sulfur appears in proteins, allowing life to function stably. Each of these elements, though not as dazzling as gold or as rare as uranium, still contributes to the stage where life can flourish. Then, at the center of massive stars, the periodic table continues to be written up to iron. But iron is not merely an end. It is a tragic milestone. While fusing atoms lighter than iron always releases energy, attempting to fuse iron requires more energy than it can provide. This is a barrier that even the mightiest stars cannot overcome in a stable state. And at this threshold, the star faces a dramatic death. The iron core collapses, a supernova explodes, or in special cases, a black hole forms. It is precisely these moments of destruction that are the climax of creation. When a supernova erupts, temperature and pressure soar to unimaginable levels, and countless neutrons are released. These neutrons strike existing nuclei, creating a nuclear storm, the rapid neutron capture process, or R process. In less than a second, elements heavier than iron, such as gold, platinum, uranium, are formed. Thus, the gold atoms you see in jewelry or the iodine atoms in your supplements all trace their origins to a moment of explosion from a distant star. Not only supernovae, but there is another rare stage, neutron star collisions. When two neutron stars spiral into each other, they create conditions so extreme that the periodic table seems rewritten in a cosmic heartbeat. Platinum, gold, thorium, and many other rare elements are born in these violent collisions. Remarkably, such events are so rare that an entire galaxy may wait millions of years to witness one. Yet the atoms in your wedding ring or phone may have been forged in one of those rare collisions, drifting through space for billions of years before landing on Earth. Looking at the periodic table, we often see a neat diagram, squares, numbers, symbols. But in reality, it is a memoir of the universe. Hydrogen and helium, traces from the Big Bang. Carbon, oxygen, silicon, stamps of stellar fusion. Iron, the limit of stellar alchemy. and heavy elements like gold and uranium, the explosive signatures of supernovae and neutron star collisions. When studying the periodic table in class, few imagine that it is a map of the cosmos, a genealogy showing where each element was born. One astonishing fact: the abundance of elements seems far from random. The most common elements, hydrogen, oxygen, carbon, iron, silicon, are exactly those needed for life and planets. This is not predestined, but simply physics. The feasible reactions in stellar cores produce them in large quantities, and life, once it emerged, learned to make use of what the universe provided. Physics leads the way, biology follows, and the result is the harmony between the laws of the universe and the emergence of life. When you pick up a rock, you are holding a piece of silicon and oxygen forged in a dead star. When you breathe, you are inhaling oxygen from an ancient stellar explosion. When you touch a gold ring, you are directly interacting with the remnants of a neutron star collision that occurred billions of years ago in some distant corner of the galaxy. In this sense, every daily action of yours is a ritual connecting with the history of the cosmos. And perhaps this is what makes science poetic. It does not strip away the mysterious beauty, but only changes the way we perceive it. Instead of seeing elements as lifeless symbols on a table, we can see them as chapters in the greatest autobiography ever written, the story of the stars, of the universe, and ultimately of ourselves. Oxygen, the element we breathe every second, seems too familiar to warrant attention, yet in reality, its story is one of the strangest epic chapters of the universe. Not only a component of the atmosphere, oxygen is a red thread running from the blazing cores of stars to every cell in your body. It is both simple and magnificent, a testament to how astrophysics and biology intertwine into a single flow. In stars, oxygen is born when carbon, the product of the triple alpha reaction, continues to fuse with helium nuclei. The conditions for this to occur are almost inconceivable to everyday intuition. Hundreds of millions of degrees and enormous pressure sufficient to bend electrostatic repulsion. Yet it is precisely in this harsh environment that a stable permanence is created. Oxygen emerges not as a fleeting flash, but as a sturdy pillar, stable enough to become one of the most abundant elements in the universe. If carbon is the architect, then oxygen is the breath. It bonds closely with carbon in organic molecules, together forming the complexity necessary for life. Oxygen is present in the glucose nourishing your brain, in proteins flexing your muscles, in ATP molecules, the energy currency of life. But to travel from a stellar core to human lungs, oxygen's journey must navigate arduous twists and turns. When massive stars reach the end of their life cycles, gravity causes the core to collapse, and the outer layers are blown into space in a supernova explosion. It is at that moment that oxygen, along with countless other elements, is released. Each oxygen atom drifts through the galaxy, joining gas and dust clouds. Millions of years later, they combine, contributing to the formation of the blue planet you now stand upon. The oxygen in your lungs today may once have resided in the core of a star that died billions of years ago. Strangely, on the early Earth, oxygen was far from abundant as it is today. The planet was initially covered by methane, carbon dioxide, and nitrogen. Oxygen existed but was locked in minerals and oceans. Only when life emerged, the first photosynthetic bacteria, was oxygen released. Each photon of sunlight split from a water molecule left a free oxygen atom. At first, this oxygen immediately reacted with iron in the oceans, creating massive iron ore bands, a geological testament to the era when seas turned red. Only after millions of years did the atmosphere truly saturate with oxygen. That event, called the Great Oxidation Event by scientists, not only transformed Earth but also shaped the entire trajectory of life. Oxygen in the atmosphere opened the path to harness energy far more efficiently than anaerobic reactions. It laid the foundation for the evolution of complex multicellular organisms. Every fish breathing underwater, every bird soaring through the sky, every human heartbeat is the legacy of this turning point. Oxygen not only sustains life, but also constructs the material environment of the planet. It bonds with hydrogen to form water, oceans covering 70% of Earth's surface. It combines with silicon to create quartz, sand, and mountains. In fact, oxygen is the most abundant element in Earth's crust, accounting for nearly half its mass. When you walk on stone or hold a glass, you are interacting with oxygen-based molecules once forged in stellar hearts. There is an interesting paradox. The invisible element you breathe is also one of the strongest corrosive agents. Oxygen breaks down iron and steel, creating rust. Oxygen burns fuel, releasing brilliant energy. Yet it is precisely this capability that has produced the diversity of the world. Without oxygen, there would be no fire, no metallurgical technology, no myriad inventions. From the primitive hearth to rockets venturing into space, oxygen is a loyal factor, always present in every advance of civilization. The balance of oxygen on Earth is a delicate play. Too much, and fires become uncontrollable. Too little, and complex life cannot exist. The 21% in our atmosphere is the result of billions of years of adjustment, a dance among biology, geology, and climate. Plants inhale carbon dioxide and exhale oxygen. Animals do the opposite. The planet functions as a giant respiratory system, with oxygen as the shared breath. When you inhale, oxygen binds to hemoglobin in the blood, transported to every cell. There, it participates in cellular respiration, burning glucose to release energy. This simple act you perform unconsciously is, in fact, a miniature copy of a supernova explosion. Oxygen releases latent energy by forming new bonds. Thanks to this, you can run, think, dream, and love. Thus, oxygen is both a cosmic legacy and the foundation of every human experience. When you look up at the sky, remember that the oxygen atoms sustaining you once erupted from the heart of a star. When you walk on the ground, recognize that the rocks, water, and air around you are all bonded by the same element. And when you breathe, consider it a direct connection between this fragile body and the entire history of the universe. Oxygen is proof of continuity, from fusion in stars, through violent explosions, to the biological cycles on the planet. It is the bridge between the distant universe and the nearest breath, and perhaps with every breath you take, you are inhaling a bit of cosmic history, a bit of the stars themselves. Iron is the period in the grammar of the universe, yet it is not an absolute full stop. It is like a crossroads, where the story of stars ends, but the story of the universe and life continues to be written. Within the heart of a star, the process of fusion gradually builds elements, like a symphony rising toward a climax. But when the melody reaches the note of iron, creation halts. The star loses the energy needed to maintain stability, and gravity, the silent yet patient companion, begins to prevail. Iron is special because it is the most stable nucleus in the entire periodic table. In nuclear physics, this means that the binding energy per nucleon in iron is higher than any other element. That is why fusing iron does not release energy. On the contrary, it requires additional energy. This absolute stability turns iron into a stopping point in the stellar cooking chain. The universe, always favoring balance, seems to have written a rule. Everything has a limit, and iron is the limit of creativity in stellar cores. Paradoxically, this very limit opens one of the most violent and creative spectacles: the supernova. When a star's core is full of iron, there is no energy left to resist collapse. In less than a second, the core collapses at an astonishing speed. Protons and electrons are compressed to merge into neutrons. The universe bends the usual laws and creates an entirely new entity, a neutron star, a sphere so dense that a single teaspoon would weigh as much as a mountain. That immense compressive force does not merely destroy, it rebounds, generating shock waves that tear the star apart from within. That moment is the supernova explosion, a dazzling cosmic firework, brighter than the galaxy it inhabits. And a miracle occurs amidst that chaos. Extreme energy and dense neutron flux create the opportunity to form elements heavier than iron: gold, silver, platinum, uranium. All are born in those brief seconds and scattered across the galaxy. Thus, iron holds a beautiful paradox. It signals the end of a star, yet it is also the beginning of the elemental richness that later forms planets, oceans, and life. Without the extreme stability of iron, a star would never reach the threshold needed to explode. Without the explosion, those precious elements would never exist. On Earth, iron is everywhere. It makes up much of the planet's core, where molten iron continuously flows, generating the magnetic field that surrounds Earth and shields life from dangerous cosmic radiation. This magnetic field is an invisible yet essential shield, preventing the atmosphere from being swept away by solar winds. In other words, the existence of breathable air, oceans, and even life itself is closely tied to the iron within Earth's core. But iron is not confined to planetary cores. It is also in your body, flowing through your blood. Each hemoglobin molecule in red blood cells has an iron atom at its center, like a gem in a biological crown. Thanks to this special bond, hemoglobin can embrace oxygen from the lungs and deliver it to every cell, then exchange it for carbon dioxide to exhale. Every heartbeat is a small song written in iron, a legacy of ancient supernovae. Imagine when you hold a rusty nail or a piece of meteorite containing iron fallen from space, you are touching the remnants of stars that died billions of years ago. When you look at a compass pointing north, you are seeing the direct trace of the colossal iron core beneath your feet. When you feel your breath quicken after a long run, that is iron in your blood at work, delivering oxygen to nourish your muscles. All of these remind us that iron is not just a metal, it is the thread connecting you to the history of the universe. There is poetry in this. Stars explode to scatter iron, and today that element helps you survive, think, and dream of those very stars. It is a circle where the death of a distant star becomes a lifeline in your bloodstream. In literature, a period marks an ending. But in the universe, iron, the full stop of fusion, is the comma of a greater story. It marks the transition from stellar stability to the violent creativity of a supernova. And from those fragments, galaxies grow richer, new planets form, and life finds the foundation to sprout. Iron teaches us a profound lesson. Even an ending can contain a beginning. The iron atom in your blood is not merely part of your body, it is a witness to a brilliant death in the distant past. When you hold an iron object, you are holding evidence of the universe's immortality, that the death of a star is not nothingness, but a promise of continuation. When we think of stars, we often see them only as distant, twinkling points of light in the night sky. Yet inside each star lies a gigantic kitchen, where the universe patiently cooks elements over millions, even billions of years. If we could slice a massive star in half, its structure would resemble the layers of an onion, each layer representing a different stage of nuclear fusion. In the outermost layer, hydrogen, the simplest and most abundant element, is compressed so tightly that nuclei fuse together, producing helium and simultaneously releasing the light we see from Earth. The deeper we go, the harsher the pressure and temperature become. Hydrogen is no longer at rest. It begins to combine to form carbon, oxygen, and other familiar elements that will later create our bones, water, and atmosphere. In even deeper layers, successive reactions produce neon, magnesium, and silicon. This process unfolds like a colossal orchestra. Each layer of elements plays its own melody, yet all harmonize into the cosmic symphony called life. However, every symphony has a final note, and for stars, that note is iron. Unlike hydrogen or helium, fusing iron does not generate energy to counteract gravity. It is the eternal wall the star cannot overcome. When its core accumulates iron, the mechanism keeping the star balanced begins to collapse. Gravity, long restrained, now seizes the opportunity, forcing the entire colossal mass to implode in an instant. Imagine a celestial body tens of times the size of the sun, in a fleeting moment, contracts into a core just a few kilometers across, roughly the size of a city. The energy released from this collapse is so immense that words fail to capture it. Protons and electrons are forced together, transforming into neutrons. The entire stellar core becomes a dense neutron sphere, so compact that a teaspoon of its matter could weigh millions of tons. This sudden halt creates a powerful rebound. Shock waves radiate outward, blowing apart the star's layers and transforming them into a brilliant explosion, a supernova. From millions of light years away, we only see a new star suddenly flash in the sky, briefly brighter than an entire galaxy. But behind that beauty lies a violent process, where energy and colliding particles tear apart old atoms and forge new ones. It is in this chaotic moment that elements heavier than iron are born. Gold, silver, platinum, iodine, uranium, the precious treasures we mine, craft, and admire, all emerge in the neutron storm of the supernova. A shiny gold ring on your hand is not merely a piece of jewelry, but also a fossil record of a cataclysm that occurred billions of years ago. The atoms composing it were once forged in the heart of a dying star. The miracle is that the fragments of a supernova do not end there. Shock waves from the explosion compress surrounding clouds of gas and dust, triggering their gravitational collapse to give birth to a new generation of stars. Thus, the death of one star becomes a catalyst for the creation of hundreds, even thousands of others. This is the endless cycle of light and darkness in the universe. Without these explosions, the Milky Way would likely be a barren galaxy with only monotonous hydrogen and helium. There would be no oxygen for breath, no carbon to build life, no iron to form rocky planets, and no gold or platinum to spark human curiosity. It is thanks to these brilliant deaths that the universe becomes rich, complex, and full of promise. Each supernova is an explosive period, yet also a beginning. From the ashes of departed stars, a new world is sown. Perhaps one day in a distant star system newly formed from the remnants of a supernova, life will also arise and wonder, where do we come from? Just as we are doing today.